Welcome everybody to the 22nd Annual Technologist Picnic. This is a new adaptation to us, having the Technologist Picnic virtually. But before I get into the formalities, I just would like to acknowledge country. So as we gather virtually from all the areas around South Central Victoria and in this case, the west of Australia and in fact overseas, we acknowledge the people of the Eastern and Western Kulin nations. In this time when our Willem camp or meeting place is dispersed across many separate homes, we hope that you all feel a strong sense of nuga or belonging in the meeting with your friends, colleagues and family using alternative and accessible communication methods. We acknowledge that the lands we're conducting our business on today remains unceded. We gratefully acknowledge the First Nations people of the 5 Kulin nations, their ancestors and elders, past, present and emerging. Well, this is both a continuation and departure for us, and we welcome all our colleagues. We thank the Australian Institute of Mining and Metallurgy, the Australian Foundry Institute, Materials Australia, Engineers Australia, the Australian Corrosion Association, and of course SEAM, the Training Centre for Surface Engineering of Advanced Materials for hosting this wonderful forum. Today we will have Professor Chris Berndt to talk about designing the face that interacts with demanding environments. Chris hardly needs any introduction. He's a distinguished professor at Swinburne University. He is the leader of SEAM and he has an illustrious career. I've got a page of details here, but he graduated in 1977 and then went on to various significant university appointments before becoming the distinguished professor at Swinburne. Just before we get into it, just some protocols. Please keep yourself on mute and without video, but please do ask questions. The chat system is set up so that you can ask questions throughout Chris's speech. At the end of his speech, I will host a Q&A when I will go through each of those questions and raise them with Chris. So we're looking forward to a very enjoyable presentation and a lively Q&A. So Chris, over to you for your presentation, and thank you very much.
Thank you. Thank you very much, Ivan, for that very kind introduction. What I intend to do over the next 30 or 35 minutes is to go through part 1, part 2 and part 3 that you see on your screen now. I'll be spending and talking a little bit about SEAM, Surface Engineering for Advanced Materials. I'll be talking about material science and engineering, and then I'll be focusing on some specific intellectual activities in part 3. Before I get too far, I'd like to dedicate and acknowledge this talk to the healthcare staff and essential service personnel who have demonstrated their commitment and self-sacrifice during this interesting period in global history. Their devotion and dedication is inspirational, and we're all stronger when we work together. So thank you very much. I too also have a welcome to country because Swinburne is located in the native nation of Wurundjeri people, and we respectfully acknowledge the elders past and present who are the traditional owners of this great land called Australia. We are honoured to recognise our connection with the Wurundjeri country, history, culture and spirituality through these locations. We also acknowledge the traditional owners of lands across Australia, their elders, ancestors, cultures and heritage. So, surface engineering, designing the face. Part 1, who we are, what we do, where we work and how we collaborate. So the first 10 minutes is really, if I could call it, a management or administrative type of talk to give you a background about how the investment from the Australian government through the Australian Research Council is being deployed through surface engineering for advanced materials. Some of you have heard a certain rendition of this late last year when I gave a talk in Melbourne. It has slightly changed, so please bear with me. So our vision statement is that SEAM trains professionals for industry. So I'll be talking about early and mid-career SEAM staff. So early career means PhD candidates, mid-career usually refers to postdoctoral fellows. And one of our intentions is to train these staff so they can be considered as plug and play by manufacturing industry. SEAM consists of 3 universities. Swinburne is the leader, RMIT University, and the University of South Australia in Adelaide. We are sponsoring 24 plus, actually 25, 26 postgraduate students. We're sponsoring 5 to 6 postdocs, 20 or so undergraduate interns. We're working with 13 companies, and we have an investment from the Australian Research Council of close to 5 billion Australian dollars. The matching funds from industry and from the universities is another $4.5 billion. And then with the in-kind package, with the in-kind cost commitments of the partner organisations and the universities, we're approaching about 18 million Australian dollars. So it's a rather large investment over 5 years. The distinctive features of SEAM are the large cohort of PhD students. So something like 85 to 90% of the funding goes directly to the ECRs, the early career researchers, and the MCRs, the 5 or so postdoctoral fellows, who are sponsored by industry and the other organisations that I'll talk about just in a little while. If you're able to fly, you'd have a 10,000-foot view of SEAM, and here it is. Specific projects are defined by industry. So these projects are at an MRL level, a manufacturing readiness level, of approximately 4 or 5. And the objective of SEAM is to get these from 4 to 5 to 7 or 8 so they can be commercialised by industry. We're training the future engineers and science leaders so they are plug and play. So they do not have to go through another training regime when they go out and work in industry. They'll be immediately helping the company. We embed our postdocs and postgraduates and undergraduates into industry. So they're embedded over their period, over their contract period for up to 12 months with industry. We're using the university resources. The university resources called the professors, senior lecturers and other academics, the staff, and using the kit, the wonderful kit that we have within the 3 universities as well as the manufacturing industries. We carry out high-level concept testing. We're carrying out immediate R&D that can be transferred straight away into industry so that they can capture IP, intellectual property, and make better products that can be distributed around the nation, around the world. The young people and the professors are innovation focused, and we're working with our industrial partners to ensure that we're doing the best. We're doing the best in the world so that we are competitive. We're leveraging technologies amongst the industry and universities, and we're applying Industry 4.0. Let me give you an idea of the timeline for how SEAM has started. So the planning started several years back. The major proposal was submitted in November 2017. The award was announced approximately 6 months later in August. 8 months later in August. There was a lot of administrative processes, a revised budget, contractual variations, a lot of participants' agreements, and then a soft launch, which implies funding started approximately in March of 2019. So you look at this from go to woe, 2 years. And people ask me, how long did it take to get SEAM going? And I say 40 years, because there are something like 40 years of effort to get to this stage where we can have the hard launch of SEAM. The original budget from the government was about 4.9 million. The original budget from the universities was about 1.7, and industry matched that. Post-award, we were able to increase that. Now, the ARC obviously don't increase because that's an award, but we were able to, on the basis of this commitment, we were able to increase the university contribution and the industry contribution. So the total budget is quite significant, and we are international, which is why I have these conversion numbers with regards to rupees, USD, euro, and the English pound. So SEAM is composed of the following chief investigators. The American, the European term would be PI, principal investigator. In Australia, we call them chief investigators. So we have people from Swinburne. The people in this shade of grey are from RMIT. The people in this darker shade of grey are from UniSA. Then we have what are called partner organisations who are contributing hard cash. Something like 15 companies, and at the top we've got the government authorities, the government national labs, our nuclear authority, our scientific authority, and then there are companies, the other 13 companies. Then there are other organisations such as Welding Australia, Materials Australia, the ACA, professional organisations, other universities from New Zealand, our Kiwi brethren, from Singapore, China, India, the Czech Republic, the USA, as well as companies in green from around the world who are contributing to SEAM, and we're all being managed by Ms. Vesna Stefanovsky, our Business and Operations Manager. Hot off the press, another organisation has joined SEAM. We've now got the AWS, the American Welding Society, being another organisation as of yesterday, and that is going to be great with regards to public relations and looking at standards and other activities. So that is the very big picture of what SEAM is composed of. If I were to get all of the SEAM people in one room, we'd have 77 bodies. So it's a reasonably large organisation, but something like 85 to 90% of the funding goes directly to the early career researchers and the mid-career researchers. So what do we do? Benefit impact, job creation, high quality workforce. We'd like to be clever. We want to be smart. Novel research outcomes for new commercial ventures. As well, there's a lot of coaching. University staff are learning how to work with industry and vice versa. Industry is learning how to tap onto and tap into the facilities and the brains within the university environment and vice versa. And we have self-sustainability. The deep detail is within the projects. I'm not going to spend a lot of time on this, but there are 13 projects and they're all interweaving to a certain extent because we can use joint kits and we can have discussions amongst ourselves. The industrial partners see that they're learning a lot from their friendly competitors. Of course, we're all competitors, but SEAM has a friendly environment and all of the companies are able to pick and choose how they can tap into their other competitors. Notice SCG Chemicals from Taiwan, from Thailand. So we have international companies who are part of SEAM and the door is very much open. Some of these collaborations involve several companies. The Defence Materials Technology Centre, fantastic. They've joined us in collaboration with McTaggart Scott, Australia, and United Surface Technologies in Melbourne. Santos, a multi-billion company. And then we've got other companies in defence areas, in the thin films, and tool manufacturing, etc. So there are many projects there. So we have what is called objectives. You may not be able to read this, but the intention is to let you know that we have key performance indicators, and I'm showing this slide to show you that we're starting to hit some goals with regards to kicking goals with regards to our funding, our primary funding agent. The Australian Research Council has approved our key performance indicators for last year, and we now have the objective of meeting our goals for the next 12 months and for the following few years. So what I've just tried to describe here is a very big picture view of how SEAM is operating. The key point with regards to part one is that the door is still open. Please contact Vesta or myself if you'd like to talk about how we can move forward. Part two, I'm going to talk about some science and talk about logos here, right? So there are many interactions with regards to Stony Brook, IIT Ropar in the Punjab, IIT Madras, UniSA, RMIT and Swinburne. So I'm going to talk about some of the specific projects which are interesting, what we know, the technologies, commercial opportunities, and in some case histories. So what do we know with regards to thermal spray? We know that if we vary temperature and velocity and look at different particles and different distributions, we can employ different technologies to get coatings via flame spray, cold spray, D-gun or plasma. Some of these are very well known. Cold spray is becoming to be very well known, but now if we start talking about cermets and ceramics, we need to apply other technologies, and this is where the new knowledge is especially important. Just to give you an idea about what these systems look like, this is a low pressure plasma spray system from Oerlikon Metco, a chamber of about 1 metre. The depth is also about 1 metre, and we're able to spray under controlled environments to get wonderful coatings which are quite dense and have low oxide contents. This process depends on temperature and velocity as these particles move down. Temperature and velocity is changing as well as the flux as the particles move from the torch head to the actual job, and we have kit, we have instrumentation which allows us to measure this. And Mitchell Sesso, unfortunately you can't see Mitchell's name down here, but Mitchell Sesso now at La Trobe University has been able to piece together this technology so that we can visualize what is happening in flight. We can look at moly particles entering into a plasma flame. Sometimes these particles hit the flame, as shown in frame A. Sometimes when this frame is frozen during this high-speed videography, sometimes the particles do not hit. So the particles can be either molten or semi-molten as they go into the flame, which is flickering like a candle in the wind, is flickering at about 3 kilohertz. So by using this sophisticated diagnostic equipment, we're beginning to understand what is happening in flight. And then we use this technology to build components. This is from the Czech Republic Institute of Plasma Physics, the water stabilized plasma. We're able to near net shape ceramic components, which are quite huge. Some of these components are meters long and are 300 to 400 centimeters in diameter with a wall thickness of several centimeters. Or we can take a cold spray system on site. This is a cold spray system taken on site to repair the piston head, the cylinder head of a very large diesel engine. And when it's taken on site, this in-site repair can be done at the cost of say $5,000 or $10,000 US to a head which will cost $50,000 to $80,000. So rather than being scrapped, you're getting some value. So I'm going to go through several history now, the third one, which are Swinburne centric. So this is work by Amy Anapunan and Ashok Megwal for extreme environments. And the application here would be for a turbine engine, either aerospace or land-based turbine. And the intention is that we're replacing the bond coat, which traditionally nickel, chrome, aluminum, yttrium. We're going to replace that with another material called a high entropy alloy. So these are extreme conditions of stress, temperature, pressure, oxidation, corrosion. And what we're doing is that we're using very complex high entropy alloys, as you see here, very complex microstructures which have a vast texture, a vast character of oxidation characters with very complex alloys, as you can see down here. And what we're doing is that we're using the sophisticated kit at Swinburne, at Madras, and at Hyderabad. We're using a sophisticated kit to identify the phase structures. So what I'm trying to demonstrate here is that we're able to join the engineering application within a turbine environment to understand the fundamental science so that we can find out how the oxidation kinetics happens within the real time of an aerospace environment. And we've published extensively in this area, thermal spray high entropy alloys, which has been downloaded 15,000 times so far, and other publications which are coming down the road. A wonderful collaboration with our Indian friends in Hyderabad and Madras in this case. Another example is that of Mr. Bruno Cole. In his example, we're talking about flight speeds of Mach 5, and we're looking at the leading edge profile of something like a vane. This is a thermal conduction problem, whereby we need to conduct heat away from this temperature, which goes up to about 3,000 degrees centigrade. So now what we're doing is we're spraying, this is called a leading edge region. We're now spraying a very interesting material called a boride. So we have a zirconium diboride or a hafnium diboride being formed in this case on a model material called either a simple mild steel or a stainless steel, so that we can eventually get to a carbon-carbon substrate, which is the real application, so that these very complex coatings can give a thermal conduction away from the leading edge. Zirconium diboride and hafnium diboride have very good thermal conductivities and good high temperature properties. And this is a project being sponsored by Wright-Patterson Air Force Base in the USA. The last case history before I start wrapping up, Mr. Chairman, is antimicrobial coatings with Mr. Farm at Swinburne. The application is quite severe, an orthopedic implant. The orthopedic implant has to undergo the design criteria, has to be quite responsive to bacteria. And what we're trying to do is we're designing the surface. We're designing the surface so that it can be antimicrobial. Of course, given this current climate, the antimicrobial application can go down many other tracks as well. So what I want you to think about here is the surface of the thermal sprayed coating. How do we design a surface to either penetrate bacteria, to have an electrostatic force to ward bacteria away, or how can we design so that we can capture these microbes? So what Farmer's doing is that we're actually spraying these coatings onto demonstration products such as knees. There's a lot of CAD-CAM, a lot of masking, so that we can actually put down a thermal spray coating to get this integrated coating. And this work is being done through the ARC Training Centre for Innovative Bioengineering, and we're working with companies such as Allegra Orthopedics and Peter Brahm in Europe. So here's a partial summary before I get to the very last part of this talk. What do we know? We know a lot about technology. We're learning more about science. We learn a lot about technologies. We know a lot about additive manufacturing. We know a lot about laser techniques. We're working with companies so that we have commercial opportunities that can be expanded via the deep science. I've given you 5 case histories. One concerned with near-net shaping, one concerned with in-situ repair, one concerned with high entropy alloys, another one on materials concerned with antimicrobial intelligent manufacturing, and another example which marries these into thermal protection systems. The very last part of the talk is what do we do in what we call the concrete tower. So please bear with me for another 5 minutes, Mr. Chairman, before we get to question and answers. So, thermal spray and actually many processes, there are many, many variables. It's a maze, it's really a jungle. How do we discriminate all of these? So what we do within our environment, within the concrete tower, is we try to understand what is happening as we inject powders, subject them to very high temperatures and velocities, and get a microstructure. That's what we're trying to do. So we have the powder injection, in-flight phenomena, and then finally the impact to get an amazing microstructure onto the substrate. So what we do then is we have a torch. We now have some kit. So we have particle velocity and temperature and particle size distribution, and we measure the temperature and thickness in situ. So we have this in-process materials control. So just to give you an example, we have a diagnostic device, and I showed you the picture before about how Mitchell put this together, Dr. Sesso put this together. So we have the temperature, the velocity, and the particle size distribution, and we put this together. Now I'm going to show you some cartoons. So here, for example, is a desirable microstructure. So by using a kit, we create this desirable microstructure. Then we start changing the powders so that we can embed a different functionality called a nanomaterial, a non-molten material, in this microstructure so that we now have a composite which incorporates both porosity and nanovoids. And now the dream is that we start fusing certain layers, changing chemistries as shown in the green renditions, so that in 3 dimensions we have something, we have a material structure which is truly complex. So I've shown you A, I've shown you C, and we get there via B. So we get from A to C via B, but the picture is as follows, is that we get controllable parameters. We measure these both online and offline to get to targeted properties. So what we're doing now is that we're using intelligent processing, we're using neural networks so that we have these feedback loops, intelligent processing. So let me wind up with the following. What we're doing within SEAM, and many universities are doing this, by the way, we're transforming science into industrial applications. If I were to try to sum up what I've done in what I've just talked about in one slide, here it is. We have many materials. We have many applications. We have thermal applications, dimensional, wear resistance, corrosion resistance. We have many applications shown in green, green, yellow, blue, pinkish, and an orange colour. And then we have all of these different materials. This is the raster. This is the portfolio of characters, the swatch of colours of materials that have been used for thermal spray. I would now like to turn the chair back to the chairman, Professor Cole. Thank you for your time, and the floor is now back to Professor Cole. Thank you.
Thank you very much, Chris. It was very enjoyable by your counsel. I've never actually said those before. That's a great challenge there. I was a little bit confused though. I've heard of ivory towers. That's what we used to reside in. What is a concrete tower?
Come to Swinburne.
Okay. I
By
think I
using the
get
term
that.
concrete, I'm trying to say more applications related. I'm trying to mesh the ivory to the applications.
That's clear. Maybe my tea is with big towers, but anyway, we do have a couple of questions, but I myself was confused. So if you want to ask questions, please go to the queue and put your questions up there. There are a couple of questions up there as well, and also that I will take my chairman's prerogative to ask a few more. But please jump on. If you put your questions up now, you'll get them answered because we have got space and time. So a couple of questions from Kieran Nagambi. The first one, how good are we now in building numerical models that predict the in-flight particle behavior in plasma spray?
The numerical models for plasma and for cold spray, for all of the thermal spray technologies, are very sophisticated. So the numerical models are good. The real question is, how do they relate to the actual practice? That's the real question. And that is somewhat variable with regards to the models which are selected. There is...
In fact, look, I'll ask another question because you're about to get to it anyway, so we can answer that one as well. So Kieran asked a second question, which is very much about what you're just about to say. How are we successful in understanding in-flight particles? And how much can we control spray parameters so that the coating is repeatable?
The control is a very fuzzy word when we talk about particles in flight. It is more of a distribution. So within a distribution, we can control them very well. The narrower that becomes more difficult.
Okay. We have a couple of anonymous questions. Has DOE been used for the matrix of thermal spray coatings?
Please repeat that question.
Yeah, it doesn't actually. Has capital DOE being used for the matrix of thermal spray coatings?
So the design of experiments techniques have been used significantly, both in full factorial and with partial box and Hunter techniques. No issues. It's quite routine within any research and development lab. Not an issue.
Okay, good. Another one from Anonymous, he's been busy, this particular Anonymous. What is the material of the bioactive coating?
Okay, thank you. I went over that very quickly. The golden standard is hydroxyapatite, which is a calcium phosphate-based material. That's the golden standard, which is used now in people. The materials that we are working on with industry in Swinburne are called bagdadite, which is a zirconium-based material, as well as strontium hardenite. Both of those materials are silicates. Those new materials are proving to be quite positive with regards to their antimicrobial, their strength and wear properties. So in summary, 3 materials. HA is the golden standard. Then there's bagdadite and strontium HT gardenite. And both of those other 2 materials are based on silicates and on zirconium.
And so just following up on that, are silicates biocompatible?
Yes.
Okay. I'll use my chairman's prerogative because so in implants, what is critical, of course, is non-bacterial growth, but on the flip side, because our own cells can grow and the rest of the bone being the known human body. Does your work also cell growth on implants?
So you're coming across a little bit fuzzy, but let me put together the few words that I heard into an answer. So what is happening is as follows, is that we are working with the microbiologists and they are doing the in vitro tests. So we're actually working with colleagues both at University of Sydney, RMIT, and at Swinburne, and they're doing the antimicrobial tests. The student FAM is learning a lot about biotechnology and biology in general. Hopefully that addresses your question, Mr. Chairman.
Okay, I'll move on because we don't have to come back to that one if we need to. Okay, this would be adopted. So I'm not quite understanding what the question is. Well, let's move this, which is when we control the coating parameters, is it possible to have a defined porosity in the thermal spray coatings?
Gotcha. Yes. So an example would be for the turbine industry, where the defined porosity for the yttrium stabilizer conia for a thermal barrier coating is between 13 to 18%. So yes, you can design the porosity. However, and this is where the science comes in, can we design the porosity size distribution? Can we design the porosity size distribution? And that is the tough question, which many people, including people like myself and people at Swinburne, are embracing. Porosity, yes. Porosity size distribution, not so easy. Okay, Mr. Chairman?
Absolutely. Just to follow on from that, can we control the porosity shape?
Wow. The answer is we have to go back. Porosity is in the form, the generic term is voids, not porosity. Voids includes cracks and porosity. So cracks can be this way or that way, and porosity can be globular or spherical. So the taxonomy of voids is very complex. Now, can we control voids? Within certain limits, yes, but it involves post-processing to get controlled networks, to control cracking, and to get what we call the, if you remember, Oswald Rightening, in order to change the globular to circular porosity. And that is another very interesting scientific topic which has technological ramifications. That is $1 million question, Mr. Chairman. Thank you.
Okay, now we seem to be running out of questions, but as a corrosion scientist, I'll ask one more question, and then we'll, during that interval, maybe somebody else might have another question. So you talked about high entropy alloys. How are they going to help my corrosion problem?
The application is for high temperature applications, oxidation. And that is why that micrograph, which I showed over, I know far too quickly, but the manuscripts are in much more detail. What we're doing is we're looking at the oxidation kinetics at medium temperature and high temperature.
Okay.
In other words, from 600 degrees centigrade to about 1100 degrees centigrade. And the oxidation kinetics of the high entropy alloys is superior to the current bill of material, which is nitroly, nickel, chrome, aluminum, yttrium. So the oxidation kinetics of the high entropy alloys is a lot better. Now, for aqueous corrosion, we are carrying out that research now, and the preliminary results are very promising.
Okay, thanks, Chris. We have one more question, so this will be the last call for questions. So if you want to have a question after this one, please put it up. So another question from Kieran. This is quite a nice produce with materials during the same process to have highly reflective coatings. It's a double barrel. Also, can we also introduce the material to have strain tolerance?
Please say that. Oh, you're coming across a little bit staggered. Please repeat the question.
Okay. Let me. Can we introduce
Give me the keywords.
Bowing process highly reflective materials doing more highly reflective coatings?
Okay, as I understand the question, we're talking about the reflective optical properties of the coating.
Yes.
The thermal spray coatings that will involve post-processing in many instances. For thermal barrier coatings, we control the surface roughness in order to look at the radiance of heat back into the environment so that we have a thermal insulation effect. For other coatings within the scene envelope, we're talking about the very thin films, the so-called PVD coatings, and those very thin films can be specifically designed to have anti-reflecting or magnetic properties, if you like, other thermophysical properties. So although I've talked about specific thermal properties, let's not forget other physics, such as magnetic, conductance, and many other properties. Corrosion resistance have already been mentioned, antibacterial properties, wear resistance, etc.
Well, thank you, Chris. I think we might close the Q&A there. We've certainly got our value. Thank you for a most excellent presentation. I even learned something, which is good for an old guy to learn something. So also I'd like to thank Gary Bunn, who couldn't be with us, but who convened this organization. And once again, thank the organizations that have hosted this, the surface engineering for advanced materials, and of course, we look forward to this, and we look forward to next year having our 22nd annual picnic, perhaps physically in Ballarat. But this has been very enjoyable. Thank you, Chris, for your inspiring talk.
Thank you.